Hello students, let's start with the next topic of our syllabus, that is nothing but a kinetic theory of gases and radiations. So if you remember, this kinetic theory of gases and radiations, basically these are the two different things. Kinetic theory is one of the theory which gives the properties of gases in terms of this theory, that comes under this kinetic theory of gases. Theory applied for the gases, that is said to be kinetic theory, because in this theory we have to consider kinetic energy only. Particles are moving with certain velocity, so at that time we assume that the particle doesn't have potential energy. That's why this name of the chapter is kinetic theory of gases. And radiation is different part, so both the topic combined together in the same chapter. So let's start with the kinetic theory of gases. And just here in the introduction part, already just they have taken a revision. Whatever the revision, whatever we have learned up till now, up to 11th standard, that part get revised little bit. What is that part they have revised in introduction chapter, introduction part of this chapter? So that if you see in your book, there are three equations, 3.1, 3.2, 3.3. These three equations are nothing but three different laws, and we can combine these three laws together and to find out the ideal gas equation. So let's first of all, let's write down the first equation 3.1 according to your book, and that is nothing but V is inversely proportional to pressure at T constant. So this is the first thing they have mentioned. Then the second they have mentioned same thing. V is directly proportional to T. V is directly proportional to T at P constant. And the third one that they have mentioned here, that is nothing but P is directly proportional to T. P means directly proportional to T at V constant. Now here, these are the three things they have mentioned. The first thing is they have told it as Boyles law. If you remember, it is a Boyles law. Might be all of you have learned this law in chemistry. Second one they have shown as a Charles law. This second as a Charles law. Might be all of you this also learn in chemistry. And third one is said to be Gay-Lussac law. So this third is Gay-Lussac law. So these are the three laws they have mentioned here. Now in this three law, what we have to see here in these three laws, before going into detail, just I have written V inversely proportional to P, T is constant. So what exactly these things? So P for pressure, P is said to be pressure of the gas, V is said to be volume of the gas, and T is said to be temperature of the gas, So these P, V, T are nothing but three parameters which give the pressure, volume and temperature of the gas. Now what is the meaning of these three laws? The first law says that volume of gas is inversely proportional to pressure of the gas, and this is valid only when, while doing this, temperature must be constant. If temperature is constant, then volume is inversely proportional to pressure. If we change the temperature, this law is not obeyed. So this is a condition. At this condition, this get obeyed. And this was first time given by Boyles. So it is said to be Boyles law. Second is nothing but this. V is directly proportional to T. Means what? Volume of the gas is directly proportional to temperature. If you increase the temperature, gas get expand. Expand means what? Its volume get increased. That is this law. Volume directly proportional to temperature. Increase the temperature, volume get increased. And while doing this, pressure of the gas must be constant. If we change the pressure, again this is not valid. So this is the second law that is said to be Charles law. And third one, pressure is directly proportional to temperature except the volume is constant. Pressure is directly proportional to temperature except the volume is constant, and this is said to be Gay-Lussac law. So these three laws might be all of you have learned in chemistry in 11th standard. If you have not learned, so just we have revised it once. Now if you combine all these three laws together, if you move this PV equal to P to this side, we can write here PV is constant, and it is constant is nothing but temperature here. P directly proportional to temperature, V directly proportional to temperature. So we can combine these two. PV is directly proportional to temperature. So this law we can write, or we can write this as PV divided by T equal to constant. If there are two pressures, P1, V1, T1 equal to P2, V2, T2 equal to constant. So these are nothing but this is the combination of these two law combined together. We can write PV is directly proportional to temperature. Same thing can be written like this. Apart from this, PV is directly proportional to temperature. This can be written again. If we take some constant of proportionality here, just remove this proportionality sign, take equality with constant. So we can write PV equal to constant, some constant is suppose R, and temperature is T. this T, and this R is called as a universal gas constant, and we know its value as they have mentioned 8.314 joule per mole per degree Kelvin. Joule per mole per degree Kelvin. This is the value of R, and is accepted universally, so it is said to be universal gas constant. Apart from this, this is the equation for 1 mole of gas. If we consider 1 mole of gas, this equation is valid. For in general n mole of gas, what we can write? PV equal to N into R into T, and might be all of you are will learn about this equation. This equation is for what? PV equal to nRT. This is the ideal gas equation. The gas which obeys this equation is said to be ideal gas. So this is ideal gas equation. This part already we have learned about. Apart from this, in this case, the value of R can be replaced just according to your book. You can write the same. This equation can be written similarly as PV is equal to R is nothing but what? It is a gas constant, and gas constant can be related to N into Kb, Boltzmann constant, here into T. N is number of molecules, Kb is the Boltzmann constant, temperature as it is. Instead of R, I have kept this. So R equal to N into Kb. This is an alternative statement of same law. Apart from here, what is meant by this number of mole N? This number of mole can be written as number of molecule divided by molecular mass. So here it is number of molecules are N, molecular mass is suppose N0, then we can represent N divided by Na, N divided by Na, N is Avogadro's number, N divided by Na is due to the number of moles. So this formula we have to use in next topics. Now after that, they have just mentioned here behavior of gas. This topic in this year from board they have removed this mean free path, so we are not going in detail. Ideal gas and real gas, what is the difference between them? Just you read it once, it is very simple to understand. So directly we jump to the next topic, 3.5, pressure of the ideal gas. So in this case, pressure of the ideal gas means what? We have to take an ideal gas in a container, and in that container we have to apply some laws, and just mathematical conversion we have to use, and we have to derive the equation for pressure of ideal gas. When ideal gas is enclosed in a chamber, and then we have to derive the equation for pressure. So I will write here pressure of ideal gas. So when ideal gas is enclosed, in your book they have taken here such type of box they have taken, that is nothing but they have taken a cube. So I will draw the cube. So let us draw the cube. So suppose this is a cube. In this cube they have just enclosed some gas. So this cube is here. In this cube gas is enclosed, and that gas enclosed is ideal gas. And this cube is such that here this is suppose x-axis, suppose this is a y-axis we can take, and suppose somewhere here it is z-axis we can take. Okay, so these are the 3 axes, or we can take the elongate this also here also, according to book, doesn't matter. So here according to book we go, it is x, it is z, it is y. I have shown y here, in your book they have shown y there. It is one and the same thing. So this is the box, or we can say cube. In this cube we have kept some ideal gas. Now here, if you consider in your book they have taken this part as a shaded one. Shaded region they have taken. So what this shaded region represent? We have to represent one side to this face of the cube. Suppose molecule are moving, to represent that this part is shaded in your book. So I have drawn this shaded portion. The cube is such that it has this length from this to this. X coordinate is L, width is L, height is again L, and here width is also, here it is L. So it is volume of this is what? L cube. So this face is L, this width is L, this height is L. So it is each unit length of L, suppose this type of cube is here. Now here we have to derive the equation. For that, let us consider when the ideal gas is enclosed in this. Let us suppose that very few amount of gas molecules are there inside. So that gas molecules are continuously in random motion. They are moving in any direction. They collide with the particle, again direction get changed, again get moved, again collide, again get changed. In this fashion the molecules are moving. So as here it is 3-dimensional cube. So it has 3 axes x, y and z. Out of that we have to consider, suppose particle is traveling along x-axis only. Particle is traveling exactly horizontal like this. It is traveling along x-axis. If it is traveling along x-axis, we have to assume that only x coordinate is changing, y and z coordinate never get changed because they remains fixed. Only particle is moving along only one axis. So one-dimensional motion we will consider, and we apply same one-dimensional motion to 3-dimensional motion. So let's start with this. So here gases are just colliding with each other, and here we have to use one approximation as they have mentioned in our book. To the first approximation, we should neglect intermolecular collision. Suppose molecule is moving from this phase to this phase. Suppose there is some collision that we have to neglect for first approximation. That collision, intermolecular collision, we have to neglect. And apart from that, what we have to consider, these collisions are elastic collisions, perfectly elastic. There is no loss of kinetic energy, and momentum of particle never get changed after and before collision. Momentum remains constant, kinetic energy remains constant, then that collision is said to be perfectly elastic collision. So these two assumptions we have to see. So there is no intermolecular collision, first parameter, first approximation. And second thing is what? The collisions are perfectly elastic. There is no loss of kinetic energy, as well as there is no change in potential. There is no change in momentum of particle before and after collision. So by using this, let's start with this. Suppose initially particle having some mass, suppose m1, here it is particle, this is a particle having a mass m1. It is moving with a velocity v1 toward the shaded phase along x-axis only. Particle having a mass m1 moving with a velocity v1 to the shaded region. Suppose in this situation, what we have to represent, we have to represent only a single thing, and that we try to correlate here. So let's start with this. So here we have taken this as a particle of mass m1 moving with a velocity v1 to the shaded phase. Now what will occur, as it is moving from this side to this side, after some time it will collide with this phase. Okay, this shaded phase, it will collide. After colliding, the same particle get rebound. Mass remains same m1. Okay, mass of the particle never get changed, it remains same. Velocity get reversed, it is minus v1, because initially going to right side, now it's coming to left side, so velocity get reversed. So here after and before collision, there must be change in momentum. That change in momentum we have to find out. So the change in momentum, I will write here, change in momentum of particle when it collide to the phase is what? Final momentum. So it is final momentum minus initial momentum. Final momentum is what? It is reverse with minus velocity, minus m into v1. Suppose the velocity is v1 and the mass I have taken m1, but mass of all particles are same because gas is same. Ideal gas it is. All gas molecule has same gas, so it has all molecule has same mass. So we can't use the m1, just velocity will write down v1. So m1 v1, final momentum, minus initial is what? M into v1, minus become plus with a minus sign, minus m into v1 plus m into v1 minus 2m into v1. So this is said to be change in momentum of particle after one collision. But we have assumed already up to first approximation, the collision must be perfectly elastic. If the collision is perfectly elastic, there should not be loss in momentum. So this minus sign should be considered as a positive, because we assume that there is no loss of kinetic energy, there is no loss of momentum. So it is plus 2 into m into v1 is nothing but a change in momentum. Now if you remember, we know the Newton's second law of motion. What is F equal to dp by dt? If you remember, rate of change of momentum with respect to time gives the force. F equal to dp by dt. We can say dp means what? Change in momentum divided by change in time. Their ratio gives the force. How much force this molecule exert on this phase, when it collide with the phase, that we have to find out, and that force is nothing but a rate of change of momentum with respect to time according to Newton's second law, and same thing, change in momentum divided by change in time. To find it out, we must find out first what is the change in time. We should find time first. We have find out the momentum. This is the momentum. Now we find out denominator, change in time, then we put both the values here, then we'll solve it further. So to solve that part, suppose before two successive collision, molecule collides here. Suppose it start here, come here. How much distance it travel? L amount of distance get travel. It collide here, again go back. Okay, so here molecule collide here, go back here, travel distance L, again come back to same place, again it will collide. So how much total distance it has traveled? So here it goes L, again come back here, it is twice L. Total distance between two successive collisions is twice L at the same point. So while doing this, so we have to find out we know the equation for velocity. Velocity is what? Distance divided by time. Distance divided by time. Our aim is to find the time. So suppose time is delta t. So we can write this as a distance divided by delta t. Find out delta t now. So delta t equal to distance traveled by the particle before two successive collision divided by velocity. How much distance that travel? Come here L, again collision, again come back here, it is twice L. So twice L divided by V. Suppose, and already we have observed that, we have found that the particle is moving along x-axis only. So what should we do? Here we have taken V1, that is component of velocity along x-axis, first particle along x-axis. So I have taken here V1. In your book they have taken Vx. So start this with a Vx here. So let's consider this as a Vx. So convert all this 1 into x. Doesn't matter. Nothing else difference is there. Instead of V1 we have taken a Vx. X velocity for x particle. X, that means particle moving along x-axis with a velocity Vx. So V1 we have replaced by Vx. That's it. So same thing. Twice L, as velocity is along x-axis, it is divided by Vx. That will give the time. Now we have the change in momentum. We have the change in time. So this is time we know, momentum we know. Then we can find out the force exerted by first molecule on this face, shaded face. Suppose that force exerted, average force exerted is F. First molecule said is F1. And it is Fx1, one particle along x-axis. It is equal to what? Change in momentum divided by change in time. This. So this thing we have to use. Change in momentum is what? 2m into Vx divided by time is what? Twice L divided by Vx. Vx goes upward. 2 get cancelled out. What we get? M into Vx square divided by L. So we get this equation, m into Vx square divided by L. Now this is for first particle, so it should be Vx1. For first particle we are writing, so we should take here it is x1, x1. So first particle. Similarly for second particle it is Vx2 square, m into Vx2 square by L, m into Vx3 by L, so on, up to n particle. And similarly this get changed. So total force along x-axis, average force exerted by all n molecules on this face along x-axis is equal to what? M by L is common in the bracket. For x1 particle Vx1 square, x2 particle Vx2 square, plus so on up to nth particle Vxn square. So this is the equation we get. Average force exerted by the n number of molecules 1, 2, 3, n on that shaded face is this much to the average force. Now we have find out the force. What is our aim? Our aim is to find the equation for pressure. We know, but we know that pressure equal to force divided by area. Okay, area of the cube is what? L square. So we can put it here. So we can write the pressure equal to F is what? Average m by L. This F will put Vx1 square plus so on up to Vxn square, okay, divide by L area. Area means it is L square. Okay, so we get this equation. Now this L comes in denominator. That L comes in denominator. So it becomes, this L comes in denominator. I will write directly m divided by L into L square is L cube. And L cube is nothing but what? Volume. That we know, that is nothing but a volume. Further, same equation can be written as m into Vx square we can write. So this as same thing, just we'll do one thing. Apart from this, as we know the square average velocity can be written as along x-axis Vx square equal to Vx1 square plus Vx2 square plus so on up to Vxn square, average velocity along x-axis. This divided by how many particles? N particle. This is the equation we know. From this equation, this is give the velocity x1 square, x2 square, xn square divided by n. From this, find out this bracket term, numerator. Numerator equal to what? Vx square into n. And that numerator here we have to put. Vx square plus Vx2 square, so on up to Vn square. This equal to Vx square into n. Put that value here. So we can write m into, what is the bracket value? Vx square into n. So that put it here, Vx square into n divided by L cube, that is nothing but a V. So we reach to this equation, that is equation 3.9 in your book. So what they have done with this equation, they have just written this equation further. I will write down to this side again now, little bit this side will go, and I will write the same thing. So just we'll make one column here. So write down the pressure P equal to, okay, so little bit goes upward, I will show it like this. P equal to, that is M into N divided by V into Vx square. That is for x-axis, particle is moving along x-axis, so Vx square we have taken. So this is the pressure exerted by all molecule. Pressure exerted by all molecule. We can take this x, all molecule traveling along x-axis on that shaded part. Px equal to Mn divided by V into Vx square. So this is the pressure. But we know one of the particle, they will exert the pressure along x-axis, that must be same. Along y-axis, that must be same. Along z-axis, that must be same. So we can write one equation as V square equal to Vx square plus Vy square plus Vz square. Velocity square must be equal to square of component along x-axis, y-axis, z-axis, their addition. So we can write this equation, and if in this case, if this V equal to Vx square, if Vx square equal to Vy square equal to Vz square equal to 1 by 3 V square. If it is equal to 1 by 3 V square, then this equation is valid. Put this 1 by 3 V square plus 1 by 3 V square plus 1 by 3 V square, it comes to be V square. That's why Vx square equal to Vy square equal to this pressure. So velocity is 1 by 3 mv square. Put this value in this equation. Write down the pressure, total pressure now. P equal to m into n divided by V. Vx square is nothing but a V square with 1 by 3 at the top. So here 1 by 3 I have taken. So this equation we get, and this is the equation which will give us a pressure exerted by all gas molecule on wall of container is equal to 1 by 3 m into n divided by V into V square. M into n divided by V into V square. Now remember, there is little bit confusion. Here there are two V. Why we can't cancel this V with this V? Because this is the velocity. Always remember, this is velocity and this is said to be volume. Don't cancel velocity with the volume. We can't cancel them. This is volume, this is velocity. This m is a mass. Mass per unit volume is what? Density. Further we can write this as 1 by 3 rho into n, 1 by 3 rho into V square. This is a further modified equation that they have not mentioned in your book. So see, number of molecule into mass of each molecule gives the total mass divided by volume. Mass per unit volume gives the density. So this is alternative equation, and this equation for pressure exerted by gas molecule when we enclose that gas molecule in a cubical container that we have seen here. Now remember, point to remember, here we have taken ideal gas in cubical chamber. You can take any shape of chamber, the equation for pressure remains constant, because this equation, there should not be change in the equation. Pressure exerted by the gas molecule on wall container never get changed. Now let's go to next topic of the syllabus, root mean square speed. Root mean square speed that we have to learn. What exactly root mean square speed that we have to see here? So let's start with the next topic of this same chapter, continue one. So it is root mean square speed. That is said to be root mean square speed. Initially they will use the word velocity. Now just instead of velocity they are just using the root mean square speed. Let's start with the RMS speed. Root mean square speed. So that was represented by VRMS. VRMS. Root mean square speed. VRMS. Now here, as we know the equation for pressure of the ideal gas, P equal to 1 by 3 m into n divided by V into V square. This equation we have derived, equation for the pressure. From this equation, just find out the value of V square. So this equation implies that V square equal to, this V goes numerator P into V, 3 goes to numerator 3 PV divided by m into n. 3 PV divided by m into n, that is the velocity square. Now here we know the ideal gas equation, PV equal to as PV equal to nRT, we know. Put that value here in the numerator, so we can write 3 nRT divide by m into n. Again, as n equal to number of mole, n divided by Na, n equal to n divided by Na, as we know that also. The n is nothing but what? Number of moles, number of gas molecules, or number of moles, small n equal to what? N divided by Na. Put it here, so we can write this as thrice small n is what? Capital N divided by Na. This R as it is, T as it is, this m into n as it is in denominator. Just what we have put here, instead of n value we have put here. Now this n cancelled out. What is remaining? Thrice RT divided by Na into m. This Na into m, it is called as a molecular weight, and that was represented by m0. So same thing can be written as thrice RT divided by m0, that is V square equal to. Now what is V? V equal to square root of thrice RT divided by m0, and this is said to be VRMS. Root means square velocity, VRMS thrice RT divided by m0. In this fashion we have derived the equation for root mean square velocity, that is nothing but a square root of thrice RT divided by m0. Apart from this, if you remember, in 11th standard in sound wave we have just find out the velocity of sound wave was represented by one equation. Velocity of sound wave equal to square root of gamma into gamma, if you remember, gamma into RT divided by m0, where gamma is Cp by Cv. Cp by Cv. The specific heat at constant pressure to the specific heat at constant volume is also always constant, that is said to be gamma, and that is nothing but this. This type of equation already we have learned. Now this is called as a adiabatic ratio. Gamma equal to Cp by Cv is said to be adiabatic ratio. Its maximum value is 5/3. That's why sound wave cannot move faster than the average speed. Sound wave cannot move faster than the average speed of the molecule, since gamma is less than 3, as they have mentioned here, and they have given here the examples. For nitrogen at 300 degree Kelvin, 300 Kelvin, for nitrogen the velocity is 517 meter per second. Just according to book, for nitrogen at 300 Kelvin the velocity is what? 517 meter per second. Same thing for, I think it is oxygen or hydrogen they have taken. What is they have taken? Oxygen, they have taken it as 483 meter per second, and all this the temperature remains constant. For nitrogen at this temperature this value, oxygen for this temperature this is the value of molecular velocity of the air particle containing oxygen and nitrogen is at this temperature this thing they have mentioned. And the last there is a little bit confusing line, I will read that. The speed of sound in H2 gas, hydrogen gas, is comparable to RMS speed of hydrogen molecule, and similarly N2 gas RMS speed of N2 comparable. The average root mean square velocity is comparable to average velocity. So this is the topic that we have seen. Now let's go to next one, interpretation of temperature in kinetic theory. Interpretation of temperature in this type of question would be asked for 2 marks. Okay, derive the equation for RMS velocity. Same thing, we have to just see now the kinetic energy. So let's start with the next topic, interpretation of temperature in kinetic energy. Temperature in kinetic energy. How the temperature is related to kinetic energy, that we have to consider here. How the temperature is related to the kinetic energy. So temperature in kinetic energy. So before we go into detail, write down the equation for pressure. P equal to 1/3 N into M divided by V into V square. This is the equation for pressure exerted by gas molecule on wall of container that we have derived. Now here do adjustment. So here we can write this as multiply and divide by 2. 2/3 into 2 by 3 n divided by v into 1 by 2 m into v square. If you see here, what I have done, 2 multiplied, 2 divided. To get cancelled out, we get same equation. I have taken m into v square in the bracket. Now we know this bracketed term, this is said to be kinetic energy in translational motion. Kinetic energy in translational motion. And in case of ideal gas, as the molecules are continuously moving and colliding and their velocity is continuously changing. After collision, velocity get continuously change. What does it means? The molecule in ideal gas, they doesn't have potential energy, they have always the kinetic energy. They never stop, they continuously moving, so they have only the kinetic energy. So we can write average total energy is therefore due to kinetic energy. So we can write one equation, E equal to average total energy of particle which are moving of the gas, average kinetic energy, average total energy of gas molecule which are in motion is always due to kinetic energy. So we can write E equal to n into 1 by 2 mv square. N is number of molecules, 1 by 2 mv square is a kinetic energy. So first molecule, second molecule, n molecule, all molecules kinetic energy, it doesn't have a potential energy. Now here, but we know from this, just if you move this v to this side, in this equation, what we can write, PV equal to, we can write this as PV equal to 2 by 3, we have moved here, it is 2 by 3 n, okay, we move to this side, 2 by 3 n into kinetic energy. So kinetic n into kinetic energy, this n into this term, this whole term, that is nothing but E. So directly we can put it as E here, 2 by 3 E. Okay, again we know, but as PV equal to nRT equal to what? PV equal to nRT equal to, for 1 mole of gas, it is RT equal to Kb into T. Na into Kb, Na into Kb into T. So it is N into Kb into T. So N into Kb into T, that we get, just a value of R is N into Kb, we have put T as it is. So that we know this equation. So we can write this as PV equal to, we can write finally PV equal to N into Kbt, this N, this equal to N into Kb into T, and that is equal to 2 by 3 E. That is equal to 2 by 3 E. Find the value of E now, total energy. So we can write here E equal to 3 by 2 PV. This is the one equation. Or E equal to 3 by 2 N into Kb into T. Or N into Kb is R, we know. We can write E equal to 3 by 2 RT. All these three equations have the same meaning. All these three equations have the same meaning. 3 by 2 PV or 3 by 2 NKBT or 3 by 2 RT. This equation they have written E divided by N number of mole equal to 3 by 2 KBT. That they have mentioned at last, so I have mentioned it here. What this equation shows? This equation shows that average energy per mole. Average energy per mole. Just I have it at downward direction. So E by N, in this E divided by N equal to 3 by 2 kBT. Average energy per mole is equal to 3 by 2 kBT. Every molecule has this much as the average energy, 3 by 2 kBT. And this average energy of the gas at a temperature T, they have given this value. So this is the part that we have learned up till now. Then after that there is a law of equipartition of energy, but this law of equipartition of energy is skip in this here. Still you have to revise it once, read it once. Still if you have any problem you can ask. In this they have mentioned degree of freedom and diatomic molecule. They are very simple. Just go through this once and try to understand this. Directly in next video we will start with the next topic, specific heat capacity, because this law of equipartition of energy is skipped this year. Okay, so directly we go to next video on the specific capacity. So first of all, watch my video. After watching, just read the same topic from your book and clear your doubt. And then next video we'll start the next topic, that is the specific heat capacity with a Mayer relation. Okay, so thank you.